Alright, so it's time in order to solve the Dirichlet integral, and the way we will do it is by using Feynman's technique. And this is just going to be a speed run, okay? So this is an even function, so I equals to integral from negative infinity to infinity of sine x over x dx is simply 2 times integral from 0 to infinity of sine x over x dx. We define the parameterized function as sine x over x e to the power of negative tx dx. Now the reason we did this was this x is kind of problematic, right? Because this just, we want to somehow eliminate this, otherwise it's going to be problematic, and no u sub is going to be combining them or them. So yeah, and so you might be saying, why not use e to the power tx? Well, if you did this, then this is not a damping function, right? This entire thing is converging, and that can be ensured directly by looking at this, because e to the power negative tx is converging since it's a damping function. So yeah, you should be always on the lookout for damping functions. Anyways, so you have to evaluate this, and since this is a damping function and this is convergent, you can just switch the order of differentiation and integration. So integration with respect to t yields negative sine x e to the power of negative tx dx. And this is, if you observe carefully, the Laplace transform for sine of x with respect to t. Recall that the Laplace of a function f of x with respect to a complex variable s is defined to be the integral from 0 to infinity of f of x e to the power of negative s x dx. And you could just find this by integration by parts, or just looking up the table of Laplace transformations. The Laplace of sine of x with respect to t would be 1 over t squared plus 1. So therefore we have that I prime of t being, remember that we have this negative sign here, so we're going to be including that, negative 1 over t squared plus 1. And holy shit, was that a cool one. Okay, cool. Now what I'm going to do is this. What I'm going to be doing is something very unconventional, but if you remember, our integral function is I of t to be the integral of I prime of t dt, and this is just indefinite integral 1 over t squared plus 1 dt, and we know this is a pretty standard integral, right? Arctangent of t plus c. We need to evaluate this c. The way we're going to be doing that is by making t go to infinity, and that is because this is a damping function, right? This is damping, and because this is damping, its graph is somewhat like this. Sorry, it just goes, and then eventually this becomes 0. So we're going to be exploiting that fact. Okay, that's not the color I wanted to use. Yeah, so of I of t would be equal to the limit of t approaches infinity of arctangent of t plus c, or you have that 0 equals, this is just pi over 2, so negative pi over 2 plus c, or c being just equal to pi over 2. Cool. So what you have is, therefore, your integral function I of t is simply arctangent of t negative plus pi over 2. How cool is that? But recall that our desired function was I of t was actually I equals to integral from negative infinity to infinity of sine x by x dx, and we modified it to make it I of t equals to the integral from 0 to infinity of sine x over x e to the power negative tx dx. So technically our target integral I is equal to twice I of t evaluated, and now we want to make this vanish at 0. So putting this over here, we have I equals to 2 times I of 0 equals 2 times of negative arctangent 0 plus pi over 2, which is just pi. So we have that the integral from 0, from negative infinity to positive infinity, and holy, that was a nice integral. Sine x over x dx equals pi. This is the Dirichlet integral solved using Feynman's technique. Thank you.